Nichols is adjunct professor of chemical biology and medicinal chemistry at the Eshelman School of Pharmacy at the University of North Carolina, Chapel Hill. Previously, he held the Robert C. and Charlotte P. Anderson Distinguished Chair in Pharmacology. He was a distinguished professor of medicinal chemistry and molecular pharmacology at the Purdue University College of Pharmacy and adjunct professor of pharmacy and toxicology at the Indiana School of Medicine, Indiana University School of Medicine. It's been a long day. So I'm just going to stop there and let people breathe while they take in what you've done and who you've been with. But there's more. Dr. Nichols joined Purdue as an assistant professor in 1974, where he remained until his retirement in June 2012. He has published more than 300 scientific articles and is recognized as an authority in psychedelics, a leader in psychedelic research globally. He is the founding president of the Hefter Research Institute, which, as you can see on the screen behind me, you'll hear a lot about tonight. So please welcome esteemed, stellar teacher and researcher David Nichols.
I'm not sure I can live up to that. I almost didn't make it. 3 days ago, I came down with the most god-awful cold I had had in a long time. I was given a lecture at Vanderbilt, and you know, when you travel through an airport, you can pick up all kinds of nasty things. And then I started having back spasms, which I haven't had for years, and I could barely stand up. So it was really touch and go, and I sent Janice an email and said, you know, I'm in really bad shape. I hope I can make it. But I've been making it. I gave 6 hours today. My voice is not what it should be, but I only have to do 2 more hours, so it should be okay. So let me start off. And it hasn't quite been 50 years. I've still got 3 more years before it's been 50 years. But I started in graduate school in 1969 studying what were called psychotomimetics. And that was the politically correct term for drugs that produce this effect. And then it became politically correct to call them hallucinogens. And now I'm trying to convince people they should be called psychedelics, because that's really, you know, a better term. So it's still controversial. In scientific terms, in scientific publications, you'll rarely see psychedelics. But I just wrote a review article on psychedelics for Pharmacological Reviews that was published, and it's the first scientific paper that I know of in a mainstream journal that has the title Psychedelics. So. Now let's see if the clicker works. Will have to be turned on. Is it? There we go. Before I start, I would like to sort of dedicate this lecture to a local icon. And a few of you know who this fellow was. Is there anyone here that didn't know Sasha Shulgin? 1 person, 2 people, 3, a few. So he was a legend in this field. He lived in San Francisco, died almost 2 years ago, had a lab behind his house, and made psychedelic chemicals and took them himself. And of course, his wife was a collaborator. If he liked the compound, then he had Anne taste it. And then if she liked it, he had a group of friends that would try it, and they would come to a consensus about what it did. And he published books describing how to make them, what the doses were, and what the effects were. So he was a kind of pioneer, one of the few people that kept this field alive, and really an icon in the counterculture. He was very revered, almost worshipped by a lot of people in this field. So just dedicate this lecture to Sasha Shulgin. And I'm not going to go through this. This is sort of the outline of what I'm going to try to cover. Background definitions, where do they come from? Beginning my career in 1969, early hypotheses, talk about some chemistry, some tryptamines, how we studied them without using humans, what were the targets, where are these receptors, how do they work, what entactogens are, and LSD and lysergamides, and some translational research. And I don't know how much of this I'll cover. I've never given a 2-hour public lecture. I've given 1-hour scientific lectures before. So I've talked to scientists so they know what I'm talking about. So a 2-hour public lecture, I'll go as slow as I can, but if I say something you don't understand, raise your hand and stop me. I don't have to cover all this. I'd rather cover a small amount really well and have people understand rather than just slam through it slide after slide after slide and just have people going, oh yeah, I didn't understand any of that. So, it doesn't look like the animations actually work. Oh yeah, here we go. So a lot of people, when they hear the word psychedelic, they think, oh yeah, you know, this guy's here and he's looking at the doctor and says some side effects. That's not what psychedelics do, although some people see things like that when they take psychedelics, but that's not what they typically do. And the definition I like was actually in a book, Goodman and Gilman's Pharmacological Basis of Therapeutics. This is the Pharmacologist Bible. And Jerome Jaffe was a drug abuse expert. And in the 7th and 8th edition, he said, psychedelics, the feature that distinguishes psychedelics from other classes of drugs is their capacity reliably to induce or compel states of altered perception, thought, and feeling that are not or cannot be experienced otherwise except in dreams or at times of religious exaltation. Now, if you were a pharmacologist, you would recognize that this is a very unusual definition for a class of drugs because there are antihypertensives, anti-obesity agents, all kinds of drugs that do things in physiology, but drugs that give you experiences that you couldn't ordinarily have unless you were dreaming or having a religious experience, that's pretty bizarre. But that's what they do, what they can do. There are psychedelics or hallucinogens, and this term entheogens has become popular, which means revealing the God within. There are a lot of people that talk about psychedelics as being entheogens. From a scientific perspective, that's probably never going to be accepted as a scientific term, but I just point out to you, these are all the same thing. It just depends on what group of people you're traveling with when they're talking about them. So they produce changes in perception, thought, feeling. They'll distort your visual space. You see curtains waving and walls breathing and things like that at low doses. They can produce feelings of portentousness. Something really important is happening. This is really an important experience. In high doses can elicit anxiety or psychotic behavior. And in people who are predisposed to develop mental illness, they can catalyze lifelong illness. In mentally healthy people, they don't produce psychosis, so they're not dangerous in that way. But some people just should not be taking these, and they may have this kind of reaction. They're not addictive, and they have very low toxicity. And when I testified in a case in Albuquerque for the UDV, they were trying to get protection for the use of ayahuasca for their church services. And there was a guy named Donald Jasinski, who was a drug abuseologist who testified before I did. He was a government witness. And he got on the stand and they said, Dr. Jasinski, why do people take psychedelics? Why do people take DMT or ayahuasca? He said, well, because it makes them feel high. They get euphoric. They really feel good. And I knew that wasn't true because they don't exactly work that way. So I went back to my hotel room because I knew they were going to ask me the same question the next day. And I thought, what am I going to say? Why do people take psychedelics? And then you could ask yourself that, why would people take a drug like that? And I woke up at 4 a.m. and I remembered something that a guy named Daniel Friedman had said back in 1984 in a book chapter. He said they produce feelings of portentousness. And I didn't know what that word actually meant at the time. And I was working with an attorney named Nancy Hollander, but it was too early to call her at 4 a.m. And this was back before we had the internet, so I couldn't look up the definition. So when I thought she was up, I called her and I said, look up the definition of portentous. So she looked it up and she says, yeah, something important, it's important, something is about to happen, it's a portentous feeling. So sure enough, when I was on the stand the next day, the first question they asked me was, Professor Nichols, why do people take psychedelics? I said, well, they take them because it feels like it's important. It produces a feeling of portentousness. They feel like it's something that's important for them to do. It's like going to church is important. Social activities are important. So it feels like it's important. So it's an important activity. And so that sort of cleared it up. And that ended that. So they produce these feelings. When people take psychedelics, they feel like the insights they get and the feelings they get are valuable, important. People talk about spiritual development. They get insights into their personality, or they see insights into the family structure. Very important insights occur. So this is one of the things that they do. There are natural sources of psychedelics. We have several. The peyote cactus, which contains mescaline. Peyote cactus is used in all-night church services of the Native American Church. They have protection under the Constitution of the Religious Freedom Restoration Act to use peyote, and it contains this compound, mescaline, and the structure was determined in 1896 by a chemist named Arthur Hefter in Germany. And then we have a variety of mushrooms of the genus Psilocybe. This is one example, and they contain tryptamines. So if we have an oxygen at this position with a phosphate group attached, that's psilocybin. And in the body, that phosphate group is cleaved to give a hydroxy here, and that's psilocin. And DMT is a really common compound that's produced in lots of plants, and it's actually in your body, produced trace amounts in the brain and cerebrospinal fluid. And it has nothing attached here, and that's dimethyltryptamine, and that's actually the active component in ayahuasca, the sacrament that the churches use, the unio de vegetal and the santo daime. And then we have lysergamides, which are derived from ergot. This is ergot-infected grain. These little black things are called sclerotia, and they're the dormant form of the ergot fungus. And if you take these off and lay them on a moist piece of paper and let them grow, they'll grow little tiny purple mushrooms. So it's actually a fungus, and this is the dormant form, the sclerotia. And during the Middle Ages, people would eat grain that was infected with these sclerotia, and they would get ergotism, or St. Anthony's fire. And if the weather in the fall when they harvested the grain was cold and moist, it would be predisposed to grow these ergot pieces. And St. Anthony's fire is a condition where the blood vessels in the fingers and toes constrict because of the presence of ergot alkaloids, and there's no blood in there, and they become necrotic and gangrenous and fall off. So people would have these stumps of fingers and toes that would come off, and they would have this intense burning sensation. So it's called St. Anthony's fire. And St. Anthony was the patron saint of people who had this. Well, if you grind these things up and extract them and treat them with lye, essentially, what you get are ergot alkaloids. And this is a typical ergot alkaloid. This is a 4-ring chemical system, and most of you probably don't know organic chemistry, so I'm going to try not to give too many structures, but when I do, I'll go slowly. So there's 4 rings hooked together. These 2 rings at the bottom are common in the tryptamines, and you see it over here. And this is called the ergoline ring system. And the ergot alkaloids from the fungus have a variety of things attached up here. And if you treat them with lye and heat, you can break them down and produce an acid, a C, there's a double bond O here and an OH here, called lysergic acid. And if you condense that with diethylamine, if these R groups are 2 carbon ethyl groups, you get LSD, which is the most notorious of the psychedelics. So it's a semi-synthetic product that's obtained from the ergot fungus. So LSD was very important, not just because it was discovered as a psychedelic, but because it catalyzed a revolution in neuroscience. So this is a structure of LSD. Albert Hofmann accidentally discovered its effects in 1943. He was a Swiss chemist. And in 1953, serotonin was detected in the brain. Now, prior to that, 90% of the serotonin is in the gut. And so everyone assumed all the serotonin's in the gut. So there was a woman named Betty Twarog, and she worked with quahogs, which is an edible mussel. And the retraction muscle in those quahogs is sensitive to serotonin. So she developed an assay by hanging these mussels up in a little organ bath, and she'd make extracts of various tissues and squirt it on, and if they contracted, it was a sign there was serotonin. And And she was working in the laboratory of a guy at the Cleveland Clinic named Irwin Page. And she wanted to test some brain extracts. And Irwin Page poo-pooed it. He says, there's no serotonin in the brain. It's all in the gut. Why would you want to do that? Well, she got some cow brain and extracted it. Sure enough, it had serotonin in it. This is 1953, 10 years later. And you can see the structural similarity between serotonin and LSD. Here's this tryptamine fragment, this 2-ring indole with 2 carbons away from a nitrogen, this 2-ring system with 2 carbons away from a nitrogen. And when people saw that, they thought, this is really interesting. There's serotonin in the brain, and they knew that LSD was extremely potent because by 1953, this was being supplied by Sandoz to investigators all over the world, and the active dose is 0.1 milligram, 100 micrograms. So prior to the 1940s, if you had a child who developed schizophrenia, it was your fault. It was the parents' fault. You had failed to nurture that child. The schizophrenia was your fault because you were a bad parent. And we had refrigerator mothers, they were called. You were cold and you were distant. You didn't raise your child right. That's why they were sick. And we had the era of psychoanalysis. Everything was psychoanalytic. And there was no notion that neurochemistry was important or even that brain chemicals had anything to do with behavior. When this discovery occurred and people realized the similarity between these two, suddenly they said, maybe serotonin has something to do with behavior. Maybe neurochemistry is important. Now that seems silly today because we know it does, but back then they didn't know. And a year later, there was a hypothesis put out by Gaddam and then Woolley and Shaw in 1954, 1955, suggesting that the effects of LSD were due to blocking the effects of serotonin in the brain. And then later that was revised to say that LSD had an effect like serotonin in the brain. But this catalyzed a revolution in neuroscience. If you go back and look in the scientific literature, no one was looking at serotonin in the brain. They were looking at norepinephrine or serotonin in the gut. When this happened, if you go back and look at the literature in the National Library of Medicine, what you see is an exponential increase in papers talking about the role of serotonin in the brain. So we have drugs today like the SSRIs for treating depression. We have the triptans for treating migraine. Those are all based on interactions with serotonin systems. So we probably wouldn't have those drugs, or we wouldn't have had them as soon as we did have them, and I'm not saying they're great drugs, but we wouldn't have had them had LSD not been discovered. So LSD was very important for this whole revolution in serotonin neuroscience, which continues today. There's an International Society for Serotonin Research, which I belong to, which continues to focus on the effects and role of serotonin in the brain. Flashback, 1962. I graduated from high school in 1962. And the police are coming for me. So I had an NSF scholarship to study chemistry at Western Kentucky State College. It's now called Western Kentucky University. And I was a geek in high school. I was the guy who made stink bombs and explosives. And I actually developed a superior technology for making stink bombs. And I've passed it on to many people. Really efficient technology. So I went to this, it was in Bowling Green, Kentucky, a couple hours from my home. And who did I meet there but 50 other guys that were just like me. And I learned how to make different kinds of rockets. I learned how to make tear gas. They all had different recipes for making explosives. Things, if I made them today, I'd be arrested. But back then, you could go to the local drugstore. I could go to the Rexall drugstore and I could buy sulfur and saltpeter and powdered charcoal, which are the ingredients for gunpowder. And the pharmacist would just wink his eye and sell it to me. So I told people at one point in time, maybe working on research in psychedelics I was making pyrotechnics for the mind. So anyway. So I started graduate school in 1969. Nobody was working in this field. Nobody was working on psychedelics or psychotomimetics at all. And I wanted to work in this field. I had a lot of friends that had gone away to college, and they started raving about LSD and mescaline and these drugs, and I started reading and said, this sounds really interesting. Where can I go study these for grad school? Nobody was doing it. There was no place. And at the University of Iowa, a guy named Joe Cannon was working on studies related to atropine. And there was a nerve gas called BZ, which is extremely potent. That's like atropine. It completely disorients you. I don't know if anybody ever had exposure to atropine, but you get completely confused. You hear voices that aren't there, you see individuals that aren't there, and you're completely out of touch with reality for a long period of time. And so I thought, well, this guy's working on those, that's the closest I can find. So I went to University of Iowa, and Joe Cannon was the department head, and he had gotten me a fellowship in National Defense Education Act, NDEA 4 fellowship. This was after Sputnik had gone up, and so they wanted to encourage people to go into college and get advanced degrees. So he got me a fellowship, and I went there, and I spoke to him. I said, I want to work on these compounds. And he said, well, I'm not working on those anymore. I'm working on these apomorphine compounds, and they're just compounds that make you vomit. And that I wasn't really interested in making compounds that made people vomit. But his grant was funded by the Department of Defense, and I surmised that they had the idea that if he came up with really potent drugs to make you vomit, you could spray it over the troops and they'd all be vomiting and they would be incapacitated. So this was kind of a disappointment, and all the literature on these compounds was published in German. And I absolutely hated German. I had to take reading German for my chemistry degree. I thought, oh my God, I'm going to have to read German and do this, and it's not, and this is really boring. And his idea was I could wrap this project up really fast and get out and get a job. Well, let me give you a little more flashback. When I graduated from high school, I was a chemistry geek, and my bedroom was a chemistry lab. And I did stuff upstairs, and my mother would holler upstairs and say, David, what are you doing up there? Close the door, you're stinking the whole house up. So my father said, well, you like chemistry, you should go and be a chemical engineer. And he didn't know anything about chemistry or chemical engineering. And if you know anything about chemical engineering, it's all math. It's designing reactors and calculating the size of pumps and pipes to make the reactors go. So I said, okay, so I went to University of Cincinnati, and they didn't have money to send me to college. I could co-op there. So I spent 2 years being absolutely miserable studying chemical engineering. And I decided, I'm not doing this. I quit, but I didn't have any money. So I thought, well, I'll get a job and I'll work, earn money, then go back to school full time. So I got a job and I started taking night classes at University of Cincinnati. They had an evening college division. You could actually get a PhD at night. So I started taking classes. But then I did something really stupid. I got married and had a child. So I thought, well, I'm not going back to school. So I just kept working. So I had a job in the daytime, and I went to night school. I took 15 hours at night school. And I worked in the daytime and went to night school for 5.5 years. And that's a job. So when I went to graduate school, I only had to take 2 courses and work in the laboratory. It was like a vacation to me. And so for this guy to tell me, like, you can do this project, you'll get out here and make money and everything, I was not interested in getting out and making money. I was interested in being in a lab and having a lot of fun for a couple of years. So these things all conspired to make me think I didn't want to work for this guy. And he said, now, even though we've written and corresponded and I've got you this fellowship, you can work for anybody you want to work for. So I talked to the other professors. One of them was an analytical chemist who I thought was doing really mundane things. And I went and talked to a guy named Charlie Barfneck, the other professor, and I'd never heard of him because he hadn't published anything. And he says, I've got a student who's making mescaline metabolites. I said, mescaline metabolites? This sounds interesting. So as I began to talk to him, it became clear that he didn't really know much about the field at all. The graduate student who was making these so-called mescaline metabolites was a really bad chemist who eventually failed out of the program. And after a short discussion, he realized I knew way more than he did about psychedelics because I had read everything that there was to know, and it was in this paper from 1969, Structure-Activity Relationships of One-Ring Psychotomimetics by Alexander Shulgin, Tony Sargent, and Claudio Naranjo. And there are 44 compounds. that was the sum total of what we knew about synthetic psychotomimetics. So I started chatting with Barfneck, and I knew this chapter and verse, and so he said, "Oh, you can work for me, yeah, you can work for me." And so I had a fellowship, and he got money, and I got money. So I went to work for him, and he just turned me loose in the lab, and I just made whatever I wanted, and we published lots of papers, and I got 16 publications as a graduate student, all on psychotomimetics. So this is how it all kind of got started. It was just really dumb luck that he was there, because he hadn't published, I didn't know he was there, and for me to have the fellowship, it just really worked out well. So sometimes luck plays a big role in your life. So Sasha had made all those compounds, and so we wanted to make a big library. There was no such thing as a Controlled Substance Act at that time. So I wanted to make a library of these compounds just so we could have them and study them. And they were easy compounds to make. And I noticed that some of these were really fluorescent, like DOM or STP. If you put that under an ultraviolet light, it fluoresces kind of a blue-pink color. LSD has intense blue fluorescence. And so I thought, and some of these had intermediate levels of fluorescence, so I thought, I wonder if there's any relationship between fluorescence and activity. So this is actually a plot, a linear plot, dose, human dose in millimoles per 80 kilograms, that's a little bit big for a person, and fluorescence intensity. So I went in and told Charlie Barfneck, my mentor, these things fluoresce. I wonder if there's any relationship. So I did a study where I looked at fluorescence intensity, and he called Sasha Shulgin up, and Sasha said, I think there's some people in Edinburgh that have found something like that. So there was a fellow in Edinburgh named John Smithies who had a real big name. And so they said, oh yeah, we've done that. So they sent us their data, such as it was. And so we published a paper. Here was DOB, and my lament, the first among you shall be the last. This was my idea. They threw in 2 or 3 compounds. I put them all together, normalized all the data, wrote the paper all by myself, and here we have Anton, Smithies, Bennington, Moore, and Barfneck, and Nichols at the very end. But that was my first publication, and that was my awakening to the role of a graduate student. So, 1969, the question I asked in the beginning and followed through for many, many years, whoa, whoa, stop, stop, stop. How did this thing do this? I can't be trusted with this clicker. I'm holding 3 things. So, the conventional wisdom at that time was that the phenethylamines, these would be mescaline analogs, related to the structure of LSD in this way. So if you think of this ring here corresponding to this ring here, and this is a 2-carbon side chain, so this is an ethylamine. It's got a methyl group attached at this alpha position, and this little wedge means it's pointing out toward you. And this is actually a diagram from a paper that we published in 1972 showing these 2 isomers. So they're optical isomers of these substituent amphetamines. This is what's called the minus or R isomer, and this is the plus or dextro isomer. And let me put some of these toys down. So you have 2 hands. You have 2 hands. You have a right hand and a left hand. They're mirror images. And if you try to put a left-handed glove on your right hand, it doesn't fit, and vice versa. So these compounds, no, I have to pick this back up. I need 3 hands. This would have been good to have a little, So these are mirror images. And you've heard of dextroamphetamine maybe. There's dextro, and it's the active one, and levoamphetamine. Well, this is dextro, and this is levo. And these are the ones that are active. And if you look at the stereochemistry of LSD, you think, well, this seems to make sense. Here's this phenyl ring, here's the phenyl ring, here's the side chain, here's the nitrogen, here's the hydrogen sticking out. Maybe this is corresponding to the methyl back here. And the stereochemistry looked like it was the same. Let's see if that works. No?
It did. Yeah, it worked. It worked.
Did it? I'm just too impatient. So there's this R stereochemistry. You couldn't get these R isomers. And you really, to really prove this, to make a library, we wanted to make a lot of them. And there was no good way to make them. So I came up with a good way to make them. I actually got a patent on this in 1976, asymmetric synthesis of phenylisopropylamines. And this is a method that was used at NIDA. They supplied these to investigators for many years. They used my patented method. I never made any money because they gave them to investigators, so they didn't make any money. But this made it available, made these isomers available so everybody could use the R active enantiomers for research. Now let me make sure I didn't miss a slide. No, okay. So I spent a lot of time over the years trying to figure out how these phenethylamines might relate to LSD. So here's DOB, and this is the active isomer. So here's LSD, the active isomer, showing the phenethylamine. Here's STP, the active isomer. So we did things to try to make these look like LSD. So if we hook this down here to make this ring, it looked more like LSD, but this wasn't active. If we tied it over here, make it look a little more like LSD, it wasn't active. We did some fancy things where we hooked this around, made it look a whole lot like LSD, where we had this oxygen instead of a nitrogen. It wasn't active. We made isomers here, they weren't active. So it was getting hard to imagine that these phenethylamines were binding to the same receptor LSD bound to in the way that people thought they did. So we also looked at what's called the lipid solubility. In order to get into the brain, a molecule has to have a certain amount of fat solubility, because the brain is fat. You know, it's 3 pounds mostly of fat and cholesterol. And activity we found was related to how soluble they were in fat. So this is a paper we published where we were just looking at these phenethylamines, trying to find out what was the role of this substituent here. So this is a compound called Aleph-1. It's a compound that I first made in a collaboration with Sasha. This is a sulfur atom, and here's its partition coefficient, which is a measure of its hydrophobicity, how lipid soluble it is. And so lipid solubility increases. A large positive value means it's very fat soluble. So there's the sulfur. Here's DOM or STP. It's a little bit more fat soluble. Here's DOB. It's a little more fat soluble. And DOI, a little more fat soluble. I think this might be LSD up at the top. So you see there's a parabolic relationship essentially showing the relationship between activity and just the lipid solubility, a real simple phenomenon that doesn't say anything about what happens mechanistically at the receptor. But this was interesting because it was giving us basic information about these kinds of compounds. So we did some tricks to make radioactive labeled ones, because to study the receptors, you need them radioactive labeled. So we took I-125 and I-123 labeled DOI. We published this with Sasha and Chet Mathis, who was out at the Donner Laboratories at that time. We also made another analog. This is 2CI. We made it labeled with I-125, developed those as tools for people to use to study this receptor more easily. Can you see me over there if I'm standing here? So we did some other tricks. And I don't know how many of you know much chemistry. How many people in here would say you have some familiarity with chemistry? Some people, okay. So how many of you that know some chemistry have heard of hydrogen bonds? Okay. So we reasoned that these methoxys, these are oxygens. So this is DOB. We reasoned that these oxygens might be hydrogen bond acceptors in the receptor. And a guy in Czechoslovakia named Miroslav Tromboda wrote to me and said he'd made a compound where he had locked this methoxy around and made a 5-membered ring here, tied it into this part of the ring, and said it was very active as a psychedelic. So we made the compound, and it was inactive. Now, I don't know what his game was, but anyway, it wasn't active. But it got me thinking, these oxygens have unshared electron pairs. If you imagine there would be two of them pointing over here, and that's actually what the hydrogen bonds are involved in. If you have a hydrogen over here, it interacts with those electron pairs. So the fact if we twisted this around so it was twisted down here, that pair of electrons that started here would switch around and be over here. So maybe it wasn't active because we needed the electrons over here for the hydrogen bonding to take place. So we hooked these methoxy groups into the ring. We did a bunch of them, I'm just showing a couple. So we tied it around into this 5-membered ring, and that forced the electrons to be in this direction. And we tied this one around this way, which forced the electrons to be in this direction. And sure enough, the compounds became more potent. The affinity for the receptor, and this is the target for psychedelics, the affinity is 1 nanomolar. That's really high affinity. And its ability to activate one of these receptors, this is a phospholipase C, the concentration, the 50% activation was 35 nanomolar. It's a pretty potent compound. Smaller numbers here mean increased potency. In this one, where we locked both of them, the affinity doubled. It went from 1 to about half, so it's twice the potency. And its EC50 went from 35 down to 8. And this compound is called bromofly, and it showed up on the black market. And then we wondered, well, if we put double bonds in here, you can't see this. This is a single bond. If we put a double bond in here, what would happen? Because it really should decrease the hydrogen bonding potential, but it'll make this molecule big and flat, very rigid, and completely aromatic. And in fact, what happened is its affinity increased by 10-fold, and its EC50 went from 8 nanomolar to 3 nanomolar. And it was twice the potency of LSD in rats in the model we were using. This is called bromo dragonfly, and this actually has killed some people, I'm sad to say. It's an extremely potent compound, one of the most potent compounds in this series. But what we've done is shown that when a flexible molecule binds, these methoxys are in this orientation, and it must be complementary to the receptor they're binding to. So at this point I thought, you know, this idea that they superimpose on LSD just isn't a valid hypothesis. They must be binding in a different orientation. It's something completely different from this flat orientation that everyone had said. So we made a number of analogs where we constrained the side chain. So one of the things I got good at as a graduate student, and even later at Purdue, was making what are called rigid analogs. If you have a flexible biologically active molecule, and you can somehow constrain it into a shape that's complementary to the receptor, it's more often more potent than not. If you don't get the shape, then that's probably not what it is. So we started designing rigid analogs to see if we could design something that was more complementary to the shape of the receptor. So we made a cyclopropane. This is a 3-membered ring. This was an active compound. We made a cyclobutane. This was an inactive compound. We made an aminomethyl compound with this one fused on here. This compound was inactive. And we probably went through a dozen series of these, making different sizes of rings, changing the stereochemistry, trying to find something that was complementary to the receptor, till we got to this compound. And this is aminomethyl benzocyclobutene. This is a 4-membered ring fused on here. Here's our 2,5-dimethoxy with a methyl or bromo over here. This is a very potent compound. It's commercially available now. It's called TCB2. It's not a controlled substance. It's one of the few compounds that scientists can get to study this receptor. Well, you can see the side chain. If you look at this, if this is a side chain, this bond here is coming out of the plane toward you, and this is swinging over here. So this is not planar at all. It doesn't lay down like LSD does. The side chain is out of plane. So if you have the plane of this ring here, this aromatic ring is here, the side chain is perpendicular. So this pretty much proved that they didn't bind in a shape like LSD. So let me just briefly talk about some excursions into tryptamines. This is a cartoon, and I don't remember what it originally said, but this is what I changed it to, from the Chef's Own Garden, Psychedelic Tryptamines. Now, we didn't do a lot of work with tryptamines. They're more difficult to modify, but there were some specific questions that we wanted to answer. And one of them was this question. So here's DMT, dimethyltryptamine, on the left. It's not active orally. You have to smoke it. This is bufotenin. It's not active orally, and I don't even think it's active if you smoke it. It doesn't get into the central nervous system very well. And this is psilocin. It's active orally, gets into the central nervous system. And you look at these and you go, what's different about psilocin that makes it orally active? Well, what we found out, or what we proposed, was that there was a hydrogen bond, that this side chain folded around and formed a hydrogen bond with that hydroxy group. So this paper is a study we did back in 1981 where we used NMR, proton magnetic resonance spectroscopy. It turns out with NMR, what proton NMR does is it looks at protons and what their relative environment is. And if you have a side chain like this that freely swings around, these protons are, these two, there are two here, they're equivalent, these two here are equivalent. But if the side chain is locked, they're not equivalent. And what we found was with psilocin, they had different chemical shifts, which suggested they weren't freely moving in solution. So something was keeping them locked. And then when we actually did some minimization, I used a program to actually calculate, it turned out there was this hydrogen bond. And this, normally a hydrogen bond will form in a ring that's 5 or 6 atoms. This is an 8-atom ring, but it seems like that's probably what happens. So why is psilocin orally active? This hydrogen bond changes the property of the molecule quite a bit. The basicity of psilocin decreases. So basicity is related to whether or not the electrons on this nitrogen are available to be protonated at physiological pH. If basicity goes down, it's not as highly protonated. Protonated molecules can't penetrate into the central nervous system. So there's actually an equilibrium. So more of this can get into the central nervous system. Also, drugs can only cross membranes if they're not protonated and they're desolvated. So in solution, normally a molecule would be protonated at physiological pH and would have water molecules associated with it. And it can't get into the brain, it can't cross membranes unless it loses that water, because the membranes are lipid membranes. So this compensates for the loss of solvation. So this has increased lipid solubility, and it's not as highly protonated. And the other, that wasn't me, I swear. And the other thing that happens is monoamine oxidase breaks down the tryptamines in the liver. And one of the first things that monoamine oxidase does is pulls an electron off of a nitrogen atom. And when we have this tied up in a hydrogen bond, that electron is not as available. So this intramolecular hydrogen bond leads to major changes, 3 major changes, so that now psilocin penetrates the CNS more easily, it's more lipid soluble, and monoamine oxidase can't break it down.
Dave, excuse me, before you go there, we have maybe a miracle here. Let's try this.
Well, you got that fixed?
Yeah, I think so. Give this a try.
This is what all the singers use, right? Look at me, I'm as helpless as a chicken up a tree. I don't know if that's a solution or not.
That was me.
Oh, that was you?
Yeah.
Oh, this will make it easier. So, if it's working, it's not working, it's sort of working, not working, sort of. I gave a lecture at Vanderbilt last week, and they were doing construction. They had a jackhammer in the back, and they had to go find the construction guys and tell them to stop. This isn't that bad. So, so I have to touch it. Let's see, it's working now. Okay, it's working for now. So
You gotta face that way.
I gotta look that way. It only works if I look at the audience.
If you stood on the other side, then you could face it.
I have a solution here suggested by Bob, which is to figure out
See if that works. See if it works. Is it working so far? Okay. Now I'll turn this way. Sort of. Sort of. No. It is what it is.
Try your right pocket.
Here. I think there's a connection problem. Is this working? It's working now. I can hold it.
Balance it on your head.
So, yeah, this works.
It really makes you smile too.
Yeah.
Rock and roll.
So I had started a collaboration with Rick Strassman, and I made DMT for Rick Strassman for that study that he published, and he decided he wanted to do a study with psilocybin, and so he asked if we could make some psilocybin. And so Albert Hofmann had made psilocybin back in the mid-50s, and he'd used a reagent. It's called dibenzyl phosphorylchloride. And this reagent is described as so unstable that if it was prepared in pure form, it sometimes would spontaneously detonate. So my technician came to me and he said, Dr. Nichols, I'm not going to make that reagent. So we spent a lot of time trying to find a new way to put that phosphate group on. Now, we found a way to do it using something called tetrabenzyl pyrophosphate. Tetrabenzyl pyrophosphate. So, yeah, whatever works, you know. Okay, so we figured out a way to put this phosphate on, and so by then Rick had sort of gotten out of the business of doing this research, so we made a bunch of it for Roland Griffiths, and he did his first study in 2006 with normal volunteers. We made the psilocybin for that study, and then we made 20 grams of psilocybin for him for a larger study, and that's what he's been using since. The psilocybin then is now being made by another company, and they charge $10,000 a gram. And I made 20 grams for $4,000. And so this will last Roland for a while. So we made a tool, and so one of the things I always like to do is make tools to help other people in this field. I used to do electronics. I should going into electronics.
Try your right pocket.
There's no pocket here.
Just connect to the other microphone.
Here. Get some really grasping with straws. There's probably a broken. Now, I've just read Janice's brain, and she's thinking, I wonder if there's a donor here who would give us money to improve our IT function.
I didn't think of that, but yes.
So I'll go back to the three-hand model. So I showed you earlier I developed a method for the asymmetric synthesis of all those isomers. Those were used. We developed a method for making I-125-DOI, which is the only non-scheduled psychedelic that scientists can use now, radioactive. And then we developed a method for making, improved method for making psilocybin, which has basically now been modified to make psilocybin for all the investigators that are doing psilocybin. So one of the things I've always liked to do is make tools for other people to speed this field along. Because frankly, there was nobody in this field. I was the only one doing this. When Rick Strassman came to me with his DMT study and said, you know, what if I get all the approvals and nobody will make the DMT? I said, well, I'll make it because I made 2 kilograms of MDMA for Rick Doblin. I can make you some DMT. And that's actually what happened. He got all the approvals and he came and he said, nobody will make the DMT. So I made the DMT. So then I made the psilocybin for Roland. Then I made a bigger batch of psilocybin. So this is a satisfying thing for me to make things that other people can use to move the field along.
What was the reagent?
Tetrabenzyl pyrophosphate. Yeah, so you take psilocin, you treat it with butyl lithium, make the lithium salt, and THF, throw in tetrabenzyl pyrophosphate, and it puts a phosphate on, a dibenzyl phosphate, and then it crystallizes, huh?
And it doesn't blow up?
No, it's a solid, it's a stable solid. I'm actually still trying to make that has 2 phosphates, and so you put one on, you lose the other. I'm actually trying to make a new phosphorylation reagent. I haven't figured out the conditions where you just have 1 phosphate. And actually, I'm trying to make it with an artificial sweetener. If you've ever looked at an artificial sweetener drink, it'll have aspartame, ace sulfame. Anybody heard of ace sulfame? Potassium ace sulfame. It's another artificial sweetener. And so I'm trying to make it out of ace sulfame because I have this fantasy of writing a paper, a new phosphorylation reagent based on ace sulfame, how sweet it is. I still want to get that done before I completely retire from the field. So anyway, so how did we assay these compounds? I hope you're having fun. I'm having fun. When I was a graduate student, if I told other graduate students at the University of Iowa that I was working on psychedelics, they always wanted to volunteer. And when I was at Purdue and they'd find out what I was doing, they always wanted to volunteer. And whenever I came to San Francisco and met people and told them what I did, in San Francisco, everybody wanted to volunteer. Well, I couldn't do that. And I was in a pharmacy school, so if I'd published stuff like that, I would have been fired forthwith. So, unfortunately, no animal model can model what happens with a psychedelic. Animals don't have these mystical experiences, they don't have these things. And I gave a talk at Stanford years ago, it was on MDMA, and Sasha Shulgin was there and some other people. There was a big symposium, and I was on the Q&A afterward, and Sasha was on the right, and I don't remember who was on the left. And somebody in the audience said, you know, we've heard all about rats and serotonin and this and that and the other, but what about the spiritual aspects of MDMA? And so I looked at Sasha and I looked at the other guy, and nobody was going to say anything, so I leaned over and I said, my rats are all atheists. But pharmacology is a science, the study of drug action, and if you want to find out what some system does in the body, you modify it with a chemical agent. So for example, if you want to know what beta-1 adrenergic receptors do in the heart, you give a drug that stimulates beta-1 receptors, and the heart rate takes off. If you want to find out what happens if you block it, you give a beta-1 blocker, and the heart rate drops off. So if you want to study consciousness, what should you use? A drug that perturbs consciousness. The best possible drugs to understand what consciousness is. Is anybody interested in what consciousness is? Yeah. Of course. 20 years ago it was taboo. You couldn't get funded. And now you have a whole branch of science called cognitive neuroscience. And I just downloaded a paper the other day from Christoph Koch and some others that was, what are the neural correlates of consciousness? And it's a review going through, like, it's a big question. What goes on in the brain? What is consciousness? And how do we define consciousness? So, how did we study these compounds? And you can't hear the sound, but this is Jefferson Airplane playing White Rabbit in the background. Somebody told me Sasha would love this if he actually saw the slide. Probably so. We couldn't do this, but I did send Sasha all the compounds we made, and he had samples of a lot of them, and they mysteriously appeared in Pical. These are a lot of the assays that we used over the years. Conditioned avoidance response in rats, smooth muscle strips. We use cats, cat limb flick. They do an interesting thing with psychedelics. Radioligand binding, conditioned place preference, in vivo knockdown, rat locomotor activity. We developed computer models of the receptor, all these things to try to find a model that we could use that was predictive or correlative with human data. And what we finally ended up with was something called two-lever drug discrimination. Now these are operant chambers. I've taken away the front so you can see what it looks like. These have levers in here that operate microswitches. And this is a trough that will deliver little sucrose pellets. 50 milligrams sucrose pellets. Sucrose is sugar. So they're rat candies. Here's an interior house light. So you can use this procedure for training rats to recognize the effect of drugs that are centrally active in humans. It's a very powerful technique, and rats will respond at doses way below those that produce any overt behavior. So suppose we want to train this rat to recognize the effects of LSD. And we did that. We trained rats to recognize LSD, MDMA, amphetamine, cocaine, you name it. You can train a rat to recognize it. So you first of all teach rats to press a lever, because they don't do that in the wild. You put them in and you teach them to press a lever in a box that just has one lever. They press the lever, they get a food pellet. They press the lever, they get a food pellet. They learn pretty quickly that if they press the lever, they get a rat candy. So then you put it into a box with two levers. A little more complicated. So now we give them an injection of placebo, saline, and we turn on the left lever, but nothing happens on the right lever. So now we put them in and they try the levers because they know if they press the lever, something's going to happen. They press the right lever, nothing happens. They press the left lever, they get food pellets or a sugar, rat candy. The next day we give them an injection of LSD. And these are very tiny injections, 80 micrograms per kilogram. And that sounds like a lot, but in a rat, that's a very small dose. And the rat doesn't feel anything. You look at the rat with that dose, they look completely normal. There's no change in behavior. Then we turn on the right lever and turn off the left lever. And now he checks the two levers out, and he finds out only if he presses the right lever, he gets a food pellet. The next day we give him a placebo saline injection, we turn on the left lever. He goes in, he presses the levers, he only gets rewarded on the left lever. So we do this back and forth, differential reinforcement, and over a period of 2 to 3 months, he reliably learns that if he gets an injection of LSD, he presses the right lever, he gets a food pellet. If he presses the left lever, he doesn't get anything. If we give him placebo or saline, he presses the left lever, he gets a pellet. This is a really robust response. We use a 15-minute training session, and these rats will push that lever 1,500 times in 15 minutes. And if you look at them, they push it with their paw, they push it with their lip, and it's like, they go nuts. Now, like most scientific equipment, these rat sucrose pellets cost us money. Much more than a big jar of candy would if you went to a candy store, because they're biomedical supplies. And so we had these rats trained on an FR10 at first, which meant fixed ratio 10. They had to press 10 times to get a food pellet. But then I hit a button. But my research associate came and said, we're really going through these food pellets fast, and they cost, I don't know how many dollars a bottle. How many times do they have to press in order to get a pellet? So we found out what's called the break point. A rat will press this lever about 75 times without getting reinforcement before it finally gets disgusted and quits. So we said, okay, we'll put them on an FR50. They have to press 50 times to get a food pellet. So we trained him on an FR50 with LSD or with other drugs. So now he presses 50 times, and he gets a rat candy. So when we get a new analog, if we think it has LSD-like effects, we give it to the rat, we put him in the box, and does he press on the saline appropriate lever, or does he press on the LSD appropriate lever? And if it has an effect like LSD, now this is very weird because everything disappeared. There we go. He says, I think you gave me LSD. And that's the way you interpret it. If he presses on the other lever, he says, I don't think you gave me LSD. So if this rat's trained on LSD and we give him amphetamine, methamphetamine, cocaine, MDMA, you name it, he will press on the saline appropriate lever. He'll only press the training drug lever if you give him something that's like the training drug. In this case, we mostly used LSD. So we had colonies of these rats. We typically had 30 or 40 rats, and we would have a colony of 12 to 15 that would be trained, say, on LSD, and 12 to 15 on MDMA or whatever. And what you could do is give different doses to the rats, and they'll give different responses depending on how big the dose is, and you get a dose response curve, and it'll give you an ED50. That is a dose that's effective in 50% of the animals, and you can correlate that. So you get a series of these dose response curves, and it'll tell you the relative potency. This is not a perfect assay. You'll get false positives, but the correlation with human activity is really pretty good in terms of potency. Again, the rat's not telling you whether he's having a religious experience. He's just saying, I think you gave me LSD. So that's the assay we use. We publish a lot of papers on that. So what's the receptor that these drugs bind to? The phenethylamines like mescaline and tryptamines, they bind to the serotonin 2A, 2C receptors. The tryptamines also bind to 1A receptors, and LSD binds to a whole bunch of them. And people used to say LSD had promiscuous pharmacology, and I said LSD has rich pharmacology. But the thing they have in common is they all activate this serotonin 2A receptor. And serotonin 2A receptors evolutionarily are very old. If you go back and look at very primitive single-celled organisms like paramecium, they've got 5-HT2 receptors in them. So this is a receptor that nature discovered early on. It works so well that it was carried forward, and we have it in our brains. It regulates sex, it regulates feeding, it regulates sleep, you name it. It regulates consciousness. So this 2A receptor is really important. It's widely distributed throughout the animal kingdom, and it's widely expressed in the human brain. So this seems to be the consensus receptor. Now LSD may do some other things, in particular activate dopamine receptors, but this is the one that they all do. The serotonin 1A receptor may affect tryptamines, may have an effect on LSD, but no one has actually dissected that down. There are studies that show that with some tryptamines, this 1A receptor is important. But basically for LSD and most of the phenethylamines, it's activation of the serotonin 2A type receptor. Question?
Yeah, maybe this is the right time. Does DMT also bind to the 5-HT7 receptor?
Yeah, the 5-HT7 is also a target for some compounds. LSD binds to the 5-HT7, but it's an antagonist. It blocks it. So it's probably not involved in the process. And there's a paper that's been published that says DMT binds to sigma receptors, but its affinity for sigma receptors is so low, it's not physiologically relevant, in my opinion. Yeah, a question?
Are there any structures of these? Do they bind the same spots? Or do they compete with each other? Maybe is another way to ask the binding.
Yeah, they all compete at the 5-HT2A receptor.
So tryptamines will compete off LSD, and all of them will compete off LSD.
Yeah, if you use a radioactive like I-125 DOI, use it to label the receptor, which is real common, you have competition for LSD and the tryptamines, they'll bind it off. And the affinities roughly correlate with their potencies. So this is like 1980, it was a picture that was done for a magazine in New York. This is the 5-HT2A receptor. And computers were really expensive and they didn't have good modeling. And I thought, you know, I bet I could build a model of this thing and figure out what happened. And so I bought, these are called CPK models. This is, you can't see the whole thing, $3,000. It was cheaper than a computer. But I thought, okay, I'll hang this up. No, there's too many degrees of freedom. This was a beautiful model. I had it in my office for a long time. A lot of people admired it, but we couldn't make anything out of it. But it was pretty. So serotonin, I'm going to say this is the fundamental molecule of consciousness. And where is the 5-HT2A receptor in the brain? It's expressed in the cortex primarily, in layer 5 of the cortex. This is the front of a brain. This is a graduate student who found out the program. We did slices of his brain and incubated him with radioactive ketanserin. And so the color here represents the density. And in the cortex, the major cells that are in the cortex that do sort of the integration are called pyramidal cells. They have a kind, you can't see it, they have kind of a triangular shape like a pyramid, and these dendrites are called apical dendrites that go up toward the outer layers. The cortex, there are 6 layers of cortex. And so these pyramidal cells are in layer 5, and these are apical dendrites. They go up to the top of the cortex. And the serotonin 2A receptors are heavily expressed on these apical dendrites. And when they're activated by a psychedelic, they depolarize the pyramidal cells. They don't actually generate an action potential, but they depolarize the membrane, so they become, the gains increased. It takes less of a signal to fire them. So what happens inside the brain cells? So if you know any pharmacology, there are 2 basic things that happen with agonists. If we're looking at a functional effect, and this is serotonin, we measure some functional effect. Serotonin will have a maximal effect, which we'll call, say, 100%, and that's a full agonist. The psychedelics basically are partial agonists. They don't achieve this full effect. And in fact, LSD is a weak partial agonist. It only achieves 25 or 30% of the effect of serotonin itself. Some of the phenethylamines like DOB or mescaline, you get almost full agonism. So LSD is kind of a conundrum. It doesn't activate the receptor to the extent you would expect, but it's very potent. So this is, you see these books like Programming for Dummies. So this is Receptor Mechanism for Dummies. These receptors are called G-protein coupled receptors, GPCRs. They bind a heterotrimeric GTP binding protein. Hetero is different, trimeric, so this means 3 different units. They have an alpha subunit, a beta subunit, and a gamma subunit. And this alpha subunit binds guanosine diphosphate or guanosine triphosphate. And in the high affinity state, the guanosine diphosphate is inside the alpha subunit. When an agonist binds, so this is serotonin, when the agonist binds, it changes the shape of the conformation of the receptor. So there are 7 of these alpha helical bundles. There are proteins that are packed inside the membrane. They cross the membrane, so we have an extracellular face outside the neuronal membrane, and this is the cytoplasmic interior face, and there are loops inside that couple to signaling mechanisms. When it's activated by serotonin or a psychedelic, there's a shape in the conformation of the peptide part that's in here that causes it to dissociate from the alpha subunit, and GDP is dissociated and GTP binds. And GTP in the alpha subunit has low affinity, so it dissociates, and so we have the alpha subunit bound to GTP, and it goes and interacts with this variety of signaling mechanisms. And this gamma beta, they stay together and they activate other signaling mechanisms. In this G-alpha subunit, it has an intrinsic enzymatic activity called GTPase, which means it hydrolyzes the GTP. and it hydrolyzes it back to GDP. So after that happens, when this GTP goes back to GDP, it has high affinity for the receptor and it goes back and reassociates. So the length of time that this alpha subunit is active depends upon how long it's got GTP in there and how long it takes that intrinsic GTPase to hydrolyze the GTP. This is actually the sizes of what those would look like. This is actually rhodopsin, which is a model. Here's roughly the size of the membrane. And this is sort of a space-filling representation of the size. And this is the alpha subunit, the beta, and the gamma. And you see if you see pictures of receptors, a lot of times they'll show this great big bundle and a little bit of G alpha, beta, gamma, like the previous slide. But actually this receptor is pretty small. It's the guts of it are inside. This is what actually creates the signal. And so the receptor just all it does is activate these subunits to produce the signals.
I'm sorry, each dot is one atom?
No, this is a surface. So there are 400 and some, probably 400 and some atoms in there. So this is just a surface. So, and these are much larger. I've covered it over with van der Waals surfaces so you can't actually see where everything is there. It would be really cluttered if you saw that.
And the colors, are they meaningful?
I've just colored them so G alpha is yellow, beta is this color, and gamma is kind of purple. So if I colored them in terms of charge, what you would see is there would be positive charges on the outside and inside. This would be all lipid-like material with almost no charges inside the membrane because the membrane is all lipid. And these would be basically mostly hydrophobic amino acids with a few polar ones. But usually in water, the polar amino acids would interact with the water, and the the hydrophobic amino acids would be wrapped inside the protein. This is actually crystal structures of the beta receptor. The inactive beta receptor is in darker color here, and the active one is in the pink. So when you activate the beta adrenergic receptor or any of these GPCRs, what you see is the top of the receptor kind of collapses around the ligand when it binds, and the bottom of the receptor actually pulls out, and you have interactions at the bottom that are important, and when this pulls out, it activates. It's part of the activation process and leads to dissociation of the alpha subunit on the inside. This may be too complex for this audience, but I just thought I'd show you some pretty pictures anyway. And this is more like what it would look like. So we did some computer simulations. So this is the bilipid layer of the membrane, and this is a receptor inside. And you can't see it in here too much, but on the top here you see a lot of blue colored things. These are charged amino groups from the phospholipid part, and they're also charged in here. So where this membrane contacts the aqueous solution, so this is extracellular outside and this is intracellular, they're polar in charge where it interfaces with the water. The interior of the membrane is all just lipid. And so in order to get into a nerve through the membrane, it has to be a nonpolar hydrophobic substance to pass through here. It can't be charged. And I've shown, so this is just a ribbon diagram, a cartoon diagram for the receptor. And these are actually cholesterol molecules, as space-filling molecules. We know that there are cholesterol molecules that also interact to stabilize this structure. So they sort of look more like this. This is just a little piece. And so when we did computer simulations, you create a box of these phospholipids. You put it into a box of water over here, a box of water over here, and then you let the computer model it. So this is sort of what it would look, a representation. This is looking at the outside, this is the receptor, and it's got a ligand bound inside, in this case. So, for those of you that took any pharmacology years ago, you were taught that a receptor was an on-off switch. So a ligand interacted with the receptor, it created a signal, and then when the ligand left, the signal ended. So things are much more complex now. When you activate a receptor, all kinds of things happen inside. So with the serotonin 2A receptor, here's an alpha, beta, gamma subunit. that would be coupled to this. This was called GQ. So there's G alpha Q, G alpha I, G alpha 1213, G alpha S, there's G alpha, there's 14 or 15 G alpha subunits. So this was the one that was thought to be most important. But then they found out it could also couple to G alpha I, and it can couple to other ones. So now when a ligand binds, it can couple to a bunch of these signaling molecules inside the cell. So imagine you have a receptor and it's got this bundle, this 7 helical bundle of protein, and serotonin binds inside. And so the receptor wraps itself around and forms a complementary ensemble around the serotonin. And that creates a particular shape on the inside of the receptor that can couple to signaling molecules. If you put LSD in there, it's a big rigid molecule. The receptor will now also wrap around LSD, but it won't wrap around the same way as serotonin because LSD is rigid. So it'll produce an ensemble with LSD in there, but the overall shape will be different. And the corresponding shape of these interior pieces of protein will be different. So this is called ligand bias or functional selectivity. So now we know that depending on what the ligand is, what the psychedelic is, it'll produce a different shape of this receptor, and that can lead to a whole bunch of different signals. So it might go through this signaling pathway, it might go through this signaling pathway. There are G-protein receptor kinases that can put phosphate groups on the interior here, and depending on where they put them, it can couple with different arrestins, which is another signaling molecule, which can generate other signals through this pathway, or it can produce internalization. The receptor can be taken inside the cell. So the situation gets more and more complex. If we want to talk about what a psychedelic does, we really don't know because there are all these possible signaling pathways. And just as an example, these are all psychedelics. They're all phenethylamines. This is DOI. This is 2CB-fly. This is TCB2. This is bromo dragonfly, bromofly. And this is an N-bone compound. These are all psychedelics. They all activate the serotonin 2A receptor. And this is called a heat map. These are 8 different signaling pathways that can potentially be turned on. And the color here determines to what extent it's turned on. So the more potent compounds are over here in lighter colors, the less potent ones are dark compounds. So for each one of these compounds, if you go across this heat map, you see it has a distinct signaling fingerprint, and they're all different. These are all psychedelics. They're all serotonin 2A agonist, but everyone is different. So all psychedelics are not created equal, we could say. So when they have different effects, we don't know what signaling pathways actually turned on, and I don't even have arrestin on here. When this was done, no one was even looking at arrestin, and that turns out to be a very important signaling pathway. And it's also chemotype selective. So if you put tryptamines in, here's DMT, and this is an analog of psilocin. In the lab where I am, they didn't have a Schedule I license for psilocin, which is the NN-dimethyl. So this is the N-ethyl methyl, which is like psilocin, has the same effect, but it's not a controlled substance. But you see, and I put serotonin here, these tryptamines all have less potency in these 8 signaling pathways. And there are more than 8. There's a large number. So the chemotype also determines that is it phenethylamine, is it tryptamine, or is it a lysergamide? So things are not very simple in terms of understanding what's going on. Which of these pathways are important? So, people still awake? I hope I'm not boring you. This is interesting to me, but I don't know if I'm keeping everybody awake. So how can a receptor signal change consciousness? This is a review article I wrote in 2004. It turns out that the serotonin 2A receptor is really important. In many organisms, what you can do is a genetic knockout. You can knock out the serotonin 2A receptor in an embryo and see what happens. If you knock out the serotonin 2A receptor in most organisms, they fail to develop at all. This is a really important receptor. It shows up in a lot of places in the brain. So all of the sensory input you get, auditory, vision, etc., goes through the thalamus, except for olfaction. That's another pathway. And there are serotonin 2A receptors here. There's the reticular nucleus, which wraps around the thalamus, and this is like a relay station. This decides what gets sent to the cortex for processing. And the reticular nucleus is loaded with 5-HT2A receptors, and it wraps around the thalamus and sends inhibitory projections in and determines also what gets sent on. The Raphe nucleus is in the brain stem. This is where all the serotonin in your brain originates. It comes from these cell bodies in the Raphe nuclei, and they fire at a very regular rate. So when you're awake, their characteristic firing rate, you can look at them if you put an electrode in an animal or in a human, they'll be firing bump, 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 bump. And when you start getting drowsy, when I'm dragging on and you're getting sleepy and you're going, God, Nichols is talking too long, your Raphe cells will go bump, bump, bump. And if you actually fall asleep while I'm talking, your Raphe cells will stop firing.
Is narcolepsy and cataplexy have to do with that?
There's probably something. I don't know the role of Raphe in narcolepsy, but probably. And the Raphe sends serotonin into the thalamus, into a lot of other areas, but also up to this apical dendrites in the pyramidal cells. And it excites these cells. It depolarizes them, but it doesn't actually generate an action potential. The nerves don't actually fire, but they become more sensitive. The gain increases. And when the Raphe cells are firing slow, you have activation of a serotonin 1A receptors, which are on these axons, and they hyperpolarize the cells. So when the Raphe cells are firing slowly, it hyperpolarizes the pyramidal cells, and they're much harder to fire. And when they start, Raphe cells fire more quickly, you get a spillover of serotonin, and now you get activation of those cells. So depending on whether they're firing quickly or slowly, you'll get activation or hyperpolarization. And these are the main computational units in the cortex. This is where everything kind of comes in. All your input comes in here. This is the executive part of your brain. This is what makes us different from earthworms, so forth, where all the executive functions are occurring. Now, the locus ceruleus has sometimes been called a novelty detector. Most of the norepinephrine that gets sent up to forebrain comes out of these cell bodies, and they're also in the brainstem. And the locus ceruleus burst fires if something novel happens in the environment. So if you have an animal that's asleep and you pinch the animal's toe, the locus ceruleus will start firing. It'll burst fire. Psychedelics don't affect the normal firing, but they enhance the burst firing of the locus ceruleus. So if this is a novelty detector, I like to think that maybe this is what happens when people take LSD and they see a flower and they've seen lots of flowers, and they look and go, oh wow, look at that. That is such a beautiful flower. Like I've never seen anything that's increased novelty. And that may be burst firing in the locus ceruleus. And it sends norepinephrine up here, and norepinephrine has alpha receptors that are co-expressed with the 5-HT2A receptors, and they share a signaling pathway. So this will have an activation effect also on these cells. And the ventral tegmental area is one of the areas, there are two, the substantia nigra and the ventral tegmental area. The VTA sends activation through dopamine pathways up in here. It's excitatory dopamine. And there are 5-HT2A receptors here. So there's a lot of feedback here going on. But basically, serotonin 2A receptors are expressed in all these key areas where cognition, memory, sensory processing occur. Now my son also does research in this area, and I've joked that he and I are going to start the Nichols serotonin mafia. But he's just found out that whereas in these apical dendrites of most of these cells, it doesn't generate action potentials. It depolarizes the cells. They become more sensitive, but they don't actually fire. There are cells in deeper layers of the cortex in an area called the claustrum that have a higher expression of serotonin 2A receptors, and they actually generate action potentials in response to psychedelics. So he thinks that they're actually the trigger mechanism. They activate, and they send glutamate up, which is the excitatory transmitter, and they get this whole thing going. So that remains to be seen. But they're also expressed. The claustrum has the highest expression density of 5-HT2A receptors in the whole brain. So And this is a simple diagram, but 5-HT2A receptors are expressed in all these important areas that are involved in cognition, consciousness, and perception. So it's maybe not surprising that when you muck around with that by giving a psychedelic, you change the way things process. And Franz Vollenweider early on used a fluorodeoxyglucose PET to show that the cortex is activated after psilocybin. So what you see is increased activation represented by these red colors, and this FDG PET shows that they're taking up glucose. So fluorodeoxyglucose can't be used by the cells. It's a positron-emitting analog of glucose, but the cells take it up as if it was glucose, and then it gets stuck in there, and you can visualize it by its radioactivity. So the cortex seems to be activated by psychedelics. So now let's switch gears and talk about ecstasy in the era of entactogens. So entactogen is a word that I coined. I don't know if you know that. But when MDMA was first becoming popular, I talked to a lot of psychiatrists, and they said, this is really an important drug. These therapists use it, and they're able to do things. People talk about repressed trauma and so forth. So this is really an interesting drug. But because it had its genesis in the black market, I said, this is never going to be commercialized. So as a chemist, can I find a way to get around that, maybe come up with something that has an effect like MDMA that's not a controlled substance? Now, Rick Doblin at MAPS is actually trying to commercialize that. He's going to make a liar out of me, which is perfectly fine with me. But at the time, in 1986, I thought, let's see if, as a chemist, I can come up with something that's different. I don't know if you've seen this card or not. And this is me. This is one of the batches. We made 2 kilograms of ecstasy for Rick Doblin for MAPS way back in 1986. And he still uses that for all the studies. They're now getting GMP ecstasy made for their phase 3 study. But all of the studies that have been published, clinical studies of MDMA, were made with this MDMA we made. This is 1/4 of, I think, of what we made. We made ultra pure material. We double vacuum distilled it, recrystallized it twice. It was 99.98% pure, good enough to use for research. So we published the first study showing that MDMA released serotonin from nerve terminals, and then we developed the second class of compounds. We said that these were representatives of a new therapeutic class, which we called entactogens. Now, many of you know Ralph Metzner, and he called these empathogens. And I thought, that from a therapeutic point of view, that just doesn't make sense. If you're a therapist and you give it to a patient, you don't want the patient to have empathy with you. Like, what is that about? And so I thought, what do these do that would be a therapeutic effect? So what I was thinking is, what they do is allow the patient to reach inside and find those things that are problematic and bring them out. So entactogen is a combination of Latin and Greek roots. Tactus is the Latin root for touching, N is within, and gen is produced. So they produce a touching within. So entactogen is the preferred term in Europe, and a lot of the scientists use entactogen, although in the popular press, I see empathogen used a lot. So we tried to prove that these compounds were not just hallucinogens. And the DEA in 1985 said MDMA is just another psychedelic amphetamine. And as a chemist, I knew that wasn't true because I knew the chemistry of these things pretty intimately. And I'll show you why, because this is the active isomer of DOM or STP. And this stereochemistry with the hydrogen sticking out at you this is the minus or R stereochemistry. This is the inactive isomer. But MDA, which is an entactogen, has the stereochemistry that's like the inactive isomer of DOM. It's reversed.
I'm sorry. Do you have an idea as to why the R-DOM is active and the S-DOM is not? Just because of the chirality?
Mm-hmm. all the receptors and biological targets in your body are made of L amino acids. So you are made of chiral stereospecific amino acids. So it's like the right glove and the left glove. You have one type of receptor, and so it's the one that's complementary with the L amino acids that make up the receptor. And that's common for all kinds of biologically active compounds.
I have another question about this, but I'll save it for later.
Okay, so the stereochemistry here is R, but the stereochemistry here is S. They're reversed. So that's the first clue. Then, if you put a methyl group onto DOM, it kills its activity. But if you put a methyl group onto MDA, it's MDMA and it's still active. And then we finally did another transformation where we looked at this alpha ethyl and alpha ethyl. And alpha ethyl DOM is inactive, but alpha ethyl here, this is MBDB, a compound we made, it's still an entactogen. And Sasha Shogun had made this compound and it had been evaluated as an antidepressant. Sasha had taken a compound and he felt kind of depressed the next day, and he'd made this compound which he called Ariadne, and he took it and it made him feel better. So he thought, well, maybe it's an antidepressant. So it was evaluated as an antidepressant by a major pharmaceutical company. They took it into a geriatric population of cognitively impaired people to see if it would help. And they inadvertently gave a dose of this to a woman of something like 340 milligrams. The dose of DOM is 5 to 10 milligrams. 340 milligrams had no effect on her at all. So the reversal of the stereochemistry, the N-methylation, and the fact that the alpha-ethyl was still active, there's no way that this fit the structure-activity relationships of a psychedelic amphetamine. It simply wasn't possible. So it has a different mechanism of action. We know it's different. We know why it's different. So then we coined this term entactogen. But then I was collaborating with a guy in Germany named Wilfried Dimpfel, and he'd been using a technique where he had electrodes planted in different parts of rat brains, and you give them different drugs and you look at the field potentials in the EEG. So these are EEG field potentials of electrodes put into the cortex, hippocampus, striatum, and reticular formation of rats. So I said, you know, we're trying to prove that MDMA is a different kind of drug. Would you mind taking your rats and giving them amphetamine, LSD, and MDMA and seeing what happens? So if you look at these patterns, you see they're very different. MDMA, if anything, looks more like amphetamine, but doesn't look like LSD at all. And this is the power, relative power spectrum in these different delta, theta, alpha 1, alpha 2, beta 1, beta 2, different frequency bends in those particular field potentials. So we published this too, showing, you know, again, there's further evidence that MDMA was a completely novel type of compound. And I don't think anybody calls MDMA a psychedelic amphetamine anymore. Some people do. Some people call it a novel psychoactive compound. I prefer to call it an entactogen because it's different. So research chemicals, let me just talk a little bit about that. We got into that a little bit. We cooked up some new stuff in the lab. Do you want to try it? And this is sort of what research chemicals are. You have these chemists in China and the Netherlands that make stuff, and they think it'll be active, and so all of a sudden it shows up on the street, spice and things like that. And people take it and they have no idea whether it's toxic or not. So some of the things we made turned up as research chemicals. And we didn't make them to be research chemicals, but this is how we got to them. When we were looking at MDMA, I wanted to find something that had an effect like MDMA, but that could be commercialized, that didn't have abuse potential. So one of the things we did is make rigid analogs. So we tied the side chain of MDMA around to make this ring, or we just hooked it directly to make this ring, or we flipped it over and hooked it this way and flipped them and reversed them to see which one was active. And you see, this is the effect of MDMA in drug discrimination in those rats. And this is the effect of this compound in drug discrimination. So we're pretty sure that it has a shape something like that when it actually binds to the transporter. And they all release serotonin, MDA, MDMA, MBDB, they all release serotonin from rat hippocampal slices that have been pre-incubated with tritiated serotonin. And their ability to produced drug discrimination in this assay is related to their ability to release serotonin. And this is actually what caused, well, let me go on and give this slide first. And then we looked at MDA and we thought, we got 2 oxygens, are they both important? Let's take one out and let's take the other out. So we have 6 APB, 5 APB. These turned into research chemicals. In that previous slide, MDAI, MMAI, PIA, 5A, these turned into research chemicals. We didn't make them for research chemicals because we were trying to figure out how these compounds worked by constraining the side chain and making analogs. But they were sold on the research chemical market. And entactogens also have effects on dopamine pathways. So the people that were looking at what we published, there was a person in the Netherlands that was interviewed, and he said, where do you get, and the woman said, where do you get the ideas for making these new research chemicals? And he said, well, we watch the things that Nichols publishes. And so then we make them. The thing they didn't understand is in drug discrimination, the rats only pick up the serotonin component. They don't pick up the dopamine or the norepinephrine component. And MDMA has an effect on dopamine and norepinephrine. So it's not the serotonin that makes you feel good, it's the dopamine release that makes you feel good. The rats don't pick that up. So when we published our studies with drug discrimination, looking at the potency here, it didn't reflect what actually made people feel good with the entactogens. So they put these things out without understanding the pharmacology.
Why do the rats not respond to the dopaminergic and...
Basically, rats pick up on the most salient cue, and for them, at least serotonin release is a thing that they can feel. With things like amphetamine, they feel dopamine, or cocaine, they feel the dopamine, but they typically only pick up on the most salient feature of what the drug does.
I have a question. What lipid source did you use for your experiments?
What source? What?
What lipid source?
Lipid source.
Yes, what was the lipid that you used in your experiments?
Lipids?
Oil. Right, like phospholipids to bind. What was the oil source you used?
In what experiment?
In your experiment, in any of your, did you not use lipids?
No.
Not at all?
No.
To bind?
No.
Okay. Then that was the question.
That's why I was confused.
Sorry, I asked the wrong one.
Okay.
Thank you.
So, entactogens, psychedelics, and psychostimulants, all basically are aryl ethylamines. An aromatic system 2 carbons away from basic nitrogen. Serotonin is an aryl ethylamine, dopamine's an aryl ethylamine, norepinephrine's an aryl ethylamine. And it just really depends upon the substituents you have on the ring that determines what the pharmacology is for these compounds. So psychostimulants increase locomotor activity, they're self-administered, they produce conditioned place preference, which is a measure of reward. I don't think I have time to talk about these. And they increase extracellular brain dopamine. So anything that makes you feel good increases dopamine in these reward centers of the brain. Cocaine, methamphetamine, a good meal, good sex, dopamine is turning over in areas of the brain. Entactogens are very similar to psychostimulants, except that they have more of a pronounced effect on extracellular serotonin release. That's what differentiates them from psychostimulants. And psychedelics have affinity for serotonin 2A receptors, and you can model them with drug discrimination in LSD-trained rats, and also the mouse head twitch, which is an interesting assay. Very fast, it doesn't require training like drug discrimination does. And if you give a psychedelic to a mouse, he'll shake his head. It's a 90 hertz frequency. And there's a guy, Adam Halberstadt at UC San Diego, that found a quick way to do this. He opens the rat's skin, he puts one of these magnets that have a high field strength. If you pick them on, you put them on the refrigerator, you can barely pick them off. I don't know what they're, niobium maybe. Puts them in there and he puts them into a tube that has a 6-inch coil, and then when they shake, it generates a current, and he can count it that way. So it's high throughput. So he's used LSD, 1P LSD, LAD, a whole bunch of things, the NBOM compounds. It's a fast method for screening. It's relatively inexpensive. And this is far away from a religious experience, obviously, but it's a model.
I think just,
Dave, we have 5 more minutes.
Yeah, I'm speeding up here, so I wasn't sure how well this would go. So how do they differ? We've talked about that mostly. I would point out that entactogens do resemble psychostimulants. They have cardiovascular side effects, and there have been people that have died from that, from the cardiovascular problems. Again, stimulants, this is kind of a summary of what I've gone through. What am I doing? I'm going backwards. Yeah, this is what happens if you give MDMA and amphetamine to rats and you put them in a box with photo beams. They run around. They don't run around if you give them saline. You give them amphetamine, they run around like crazy. Give them MDMA, they run around, but not quite as much. And you can block it with an alpha receptor blocker. So I don't know if I want to. We have 5 minutes. I should probably stop. The N-bone compounds, you've heard those are not that important. Yeah. It was hard for me to know 2 hours in. Yeah, some interesting stuff here. What was it? I'll have to come back next year and give the other half of this talk.
Yes.
Yeah, sorry about that. Yeah, this is really interesting stuff. Yeah. I had never given a 2-hour public lecture, and I just finished giving 6 hours to the certificate class, and I was afraid it wasn't long enough, but it worked out just right. But this obviously was a 3-hour talk instead of a 2-hour talk, so I really apologize. But we've gone all the way from trying to figure out how phenethylamines bound like LSD to deciding they didn't bind. These slides that I went through at the end, basically we have computer models of that receptor now. We can do virtual docking. We know some of the things that happen in the receptor. We know why LSD gets in the receptor, and LSD actually, in data that haven't been published, it's been submitted to Nature about 3 weeks ago, LSD actually gets trapped in the 5-HT2A receptor and doesn't come back out for like 10 hours. So it's a really interesting phenomenon. So translational stuff, I should just mention a lot of stuff the Hefter Institute has done with psilocybin, ongoing studies. You've probably seen a lot of this stuff. Whoops. Well, I could have deleted this slide too. And then my postdoctoral mentor, J.P. Long, told me he never thought I'd get funded to work on psychedelics. So I really apologize for not having time to cover everything. You know, well, almost 50 years trying to compress it into 2 hours, and I only compressed it into 3 hours. So anyway, thank you. This is the. This is actually kind of a record. In all the years I've given seminars, I've never given a seminar where I had 30% more material than I could present. So I really apologize for that. I'm usually much better.
I got a quick question. You said that LSD binds for 10 hours, it gets stuck. Are there competitive inhibitors that'll knock it off?
No.
Or they're not? So there's no reversal really? There's nothing that can, and do you know what, like why does it come off eventually?
It turns out that the receptor, there's a loop that connects the top of helix 4 to helix 5. It's called extracellular loop 2. And there's a residue in there, a leucine 229, that when LSD gets into the receptor, that loop folds over the LSD and it sticks in there. And we've actually done studies where we mutated that leucine to an alanine, and LSD pops back out when you do that. So we know there's a specific residue. So what I would have shown you, and I could have eliminated this early stuff and focused on the LSD stuff. What we really found was that those compounds got in there, stayed in there, didn't come back out, and that may be the reason LSD acts for such a long period of time, because normally serotonin gets in the receptor and within 5 minutes comes back out. Most ligands will get in, get back out, but LSD gets in and takes 10 hours to get back out. So, yeah, I had to come back.
15 minutes for questions.
Yeah, we have lots of, yeah, we can get questions. Yeah.
You mentioned there had been some fatalities with Romo dragonfly. Do you think
properties, or what do you think's going on with those?
There are serotonin 2A receptors in the vasculature,
Yeah.
and with bromo dragonfly, I suspect that may be what happens.
Okay.
It causes vasoconstriction, but I'm not sure. The autopsies are not clear.
Mhm.
These N-bone compounds are the same situation where they are extremely potent, 10 times more potent than anything we've seen, and they also may get in the receptor and produce prolonged vasoconstriction and then hypertensive crisis.
Hi, thank you. The alpha beta blocker that seemed to help calm the rats, I don't know if calm is the right word, but so for the kind of hangover effects of MDMA for humans, would an alpha receptor blocker make sense for humans to maximize the experience?
So with prazosin as an alpha blocker, and we pre-treated the rats with prazosin because we had the hypothesis that norepinephrine was also important to the action of MDMA. So we pre-treated with prazosin and we blocked that effect. So what we showed was that norepinephrine was important for the psychostimulant effects. So MDMA releases serotonin, dopamine, and norepinephrine. So we showed that we could block some of the hyperlocomotion by using an alpha blocker beforehand. Someone asked me earlier today whether giving an SSRI 3 or 4 hours after taking MDMA could prevent this postulated neurotoxicity, and probably can. The mechanism, we believe, is that the serotonin terminals get depleted of serotonin by MDMA, and then they take up dopamine. And dopamine is a really toxic neurochemical. It oxidizes and forms quinones and radicals, and serotonin terminals don't have the ability to take care of that, whereas dopamine terminals do. So it damages the terminal. So an SSRI would block the transporter and keep the dopamine from getting in there. So if I were going to talk about a potential mechanism for preventing day after stuff, it would be to take an SSRI. But I'm not a doctor, I can't tell you to do that.
What is your sense for the future of psychedelic research in the United States?
The future of psychedelic research in the United States, we have 2 big papers that will be published on treating end-of-life patients with psilocybin, one from Johns Hopkins University and one from New York University. There's a big study of alcoholism that's going on now. It started at New York University that'll have 90 alcoholics and 90 placebo. There's an expanded study treating people who are addicted to cigarette smoking, a larger study now. There's a study in Alabama Peter Hendricks is doing, looking at psilocybin to try to disrupt cocaine addiction. If these studies all turn out to give the kind of results we've gotten with things so far, it's going to be a paradigm shift for psychiatry. And I tell people, I don't know a whole lot about paradigm shifts, the structure of scientific revolutions, but I think we're on the verge of that. In the 1950s, psychiatry hailed the advent of psychedelics, most particularly LSD, as the new technology for psychiatry. And if you've read Grinspoon and Bakalar's book, they say there were 1,000 papers published describing 40,000 patient treatments with LSD, and that was the new technology for psychiatry. And then we had Leary and the Controlled Substance Act, and it all was killed. And I think that what we're going to see is when these studies start being done, we're actually going to see that these drugs do the things that many of the things that people thought they would do. And so what we've had is this 50-year hiatus, which was caused by politics interfering with science. So I think we'll see that in our lifetimes. I think we'll see these things being used. When you can take somebody who's been depressed, well, in the UK they have an open label study of chronically depressed patients who don't respond to any medication. And they gave them 10 milligrams of psilocybin, and then a week later gave them 25 milligrams. And I saw the 3-month follow-up. Most of them are still not depressed after 3 months. And Robin Card Harris said he had a 52-year-old patient who was given that treatment. He said, "This is the first time in my life I can remember that I haven't been depressed." So this is not like an SSRI. SSRIs work in 40 or 50% of the people, and they work better if there's a little therapy. But they're not that good, and they've got all these side effects. If you can give somebody psilocybin once or twice and they're not depressed anymore, I mean, that's a revolution. Anxiety, same thing. If we can treat alcoholism, same thing. So it's really going to change psychiatry. Psychiatry is a very conservative profession. You know, they change very slowly, and there's still resistance. We're, you know, in terms of getting things published, getting grants published, there's still, the people in those institutes are worried that the Republican politicians are going to find out we're giving psychedelics to sick people and say, what are you doing? And that hasn't happened. I'm hoping we get enough of a database before that actually happens. But I think we're going to see a change. I think it's a paradigm shift, and we're going to see it happen. This is going to be a new modality for treating people who aren't treated well by conventional medications for an awful lot of things. It's going to take a while, 10 years, 15, 20 years, but within most of your lifetimes, maybe within my lifetime, you know. But I think we're going to FDA for phase 3 guidance for psilocybin for end-of-life distress. And if we get approval to do the study, it probably takes 5 years. So 17 and 5, 2022 maybe. So sometime in the 2020s, and I think Rick Doblin thinks 2023 maybe MDMA will be out for PTSD. So mid-20s, we might start seeing that. People are starting medical school now and go 4 years of medical school, 2 or 3 years of residency. When they get out, there may be places for those people to be psychedelic therapists. So that's what I hope. Yeah.
I heard a shaman friend of mine, excuse me, I heard a shaman friend of mine say, in response to a question a young woman asked, she said, how long will this last? And he said with a twinkle in his eyes and a big smile, forever. And my observation has been that people who have used and reflected on their use of the psychedelics, they've discovered that they think they are different than other people who haven't. They seem to see their path in life be different. I'd like to know, have you seen anything different about your mice? Because I know, or your rats, because I assume you haven't been doing human studies.
No, the rats don't change. You know, one of the personality traits, though, in the study that Roland Griffiths did in normal subjects who they gave psilocybin, personality is considered to be fixed from the time about age 2 or 3, and there are very few things that can change your personality. And you know, traumatic events can, major things can, but not much. Basically, personality is fixed. And one of the things they found is that in a 14-month follow-up with people who had this mystical experience, the personality trait of openness was increased. And openness includes, increased humanity, altruism, openness to new ideas, progressive ideas. So people who have that experience, they are changed. Their personality is changed. So people who take psychedelics and have a good experience basically become, in my opinion, better people, or can become better people. I've known a lot of people who use psychedelics who were complete jerks, but it's possible.
If we have time for one more question.
Okay.
So I have the mic.
Oh, you have the mic, so you're in command.
I am a budding psychiatrist, but was also a biophysicist in a past life. And I think this issue of sort of timing is really interesting to me, right? So depressive states, anxious states, these are typically very chronic states. And when I think about a drug like an SSRI, it takes 6 weeks to work. And that sort of conceptually makes sense to me because things have to change in the brain for the person's emotional state to change. And what I can't reconcile yet is how is it that with a single experience, with 2 experiences, it's possible to achieve a different emotional state. It's possible to bring someone out of a depressive episode. I mean, just sort of thinking about the cell biology that has to happen for that to be true, it seems like a single round of LSD binding to 5-HT2A receptors should not be sufficient to do that, and so I'm struggling to like explain to myself these sorts of issues of time.
So what are your thoughts about a single injection of ketamine having an antidepressant effect within 2 hours?
No, that's fair enough. I'm not. I mean, I think it's. I have a similar. I don't know, similar set of questions about ketamine. It's not LSD or, it's not specific to LSD. And I guess, you've spent a lot of time thinking about the pharmacology and seemingly the cell biology, or at least the signal transduction part of it. What are your thoughts? How do you get a long-lasting effect based on one pulse of LSD binding?
I think
or MDMA, whatever.
it's part of the paradigm change. As a pharmacologist, I always tended to think of anxiety, benzodiazepines, depression, SSRIs. I tended to think of a receptor mechanism. And a couple weeks ago, I started thinking, what could happen in the brain that a psychedelic could do that could alleviate depression, anxiety, disrupt alcohol addiction, disrupt nicotine addiction, potentially OCD? It's not a receptor mechanism. There's something else going on. And I used to tell people, I think it's like rebooting the computer. You hit Control, Delete if you have a PC. I don't know if you does a Mac ever crash? They do, I know. But, yeah, I know they do. And so Robin Card Harris gave a talk in Copenhagen, and they asked him, like, how does this work? And his next slide was a big slide that had a big red button with the white letters reboot on it, a button. He said it somehow reboots the computer. Now this latest paper he published where they looked at LSD, what they did was they identified functional connectivity in 12 different areas of the brain. These were areas that were communicating. And when the LSD was given, there's the default mode network, which is sort of the resting network. It disintegrated. And all of these 12 functional connectivity networks also disintegrated. They lost their functional connectivity and they became all connected together. So there was this increase in connectivity. He calls it an entropic brain. There was an increase in level of entropy. So all the little modular connections broke down. Everything became connected. And he said, maybe this is what happens when you have ego death and you experience there's no boundary between you and everything else. So you have a disruption of all these modular functional connectivity groups. And the peak experience is the effect of this ego loss, the disruption of the default mode network, and then everything being all connected. And then when the drug wears off, things reconnect. And maybe they reconnect in the way they're supposed to be. So people that have depression have a dysfunctional functional connectivity in the limbic circuit, and in depression you have and they're doing studies with functional connectivity, and they know that depressed people and anxious people and addicted people, they have these functional connectivity circuits that are abnormal. So maybe when you just completely shatter that and everything becomes entropic and chaotic, when it comes back together and puts itself back together, maybe those dysfunctional routines are gone. So maybe it's actually a good analogy like the Control, Delete, where you've got dysfunctional subroutines that are hogging the memory and causing these problems, and they just disappear. So I think we'll have to get away from thinking of a mechanism. The 5-HT2A receptor activation is what causes the disintegration of these networks, allows everything to communicate, and then when it reassembles itself in a way where these dysfunctional connectivity networks are lost. So that's what I think probably happens, but we're away from understanding that. But I think it's going to give us a completely different idea about what these diseases are, how they can be treated, and get away from the idea of blocking, the serotonin reuptake carrier and blocking benzodiazepine receptors to block. I think we have to kind of get away from that paradigm and think more about functional connectivity and how that's being altered by these experiences. So that's what that would be my explanation. Again, I really apologize for not having better timing. I was sick the week before I came, and I normally would go through and I would time a seminar and see how long it takes. And I had back spasms, I had this horrible upper respiratory thing, and I just didn't go through and time it, so I apologize for that. I usually...
We'll have you back. We'll
Okay,
have you back.
it's a deal.
Yes, thank you.